students, the purpose of this video is to get you acquainted with probability, and this is set 2 of your notes. The very first term that we're going to talk about is the complement. This is the idea of what does not occur. So we've talked about notation in set 1 video, but we're actually going to introduce a new, more formal notation. It is a tick mark on the event, and it looks like this. You see that I've circled it there, and I have this little tick mark that I'm drawing an arrow to. Therefore, if I want to find the probability of what's not going to occur, the formula that I use is 1 minus the probability of the event actually occurring. And this makes sense because I know that the total probability of an event, the total value possible is 1 because that's the largest value we can take on. And then we subtract off the probability of what we know the probability of an event is, and that's going to get us what's left over, which in this case is going to be what does not occur. And let's actually, because I don't believe I've written an example, so let's actually do one. Let's say we are going to roll a die, and we are going to find the probability of not getting an even number. So I'm going to do an even with a little tick mark to show that I am looking for not even. So to find the probability of not even, I'm going to do 1 minus the probability of being even. And if I'm rolling a die, my sample space would be 1, 2, 3, 4, 5, 6. Those are all my possible outcomes that I could get. And for the values that are even, there is 2, 4, and 6. So that's half. So 1 minus half is actually equal to 1/2. So the probability of not being even is supposedly 1/2. And let's verify. 1, 2, 3 out of 6. So sure enough, that formula does work. Now, looking at tree diagrams, this is one way that we can also find probabilities. It's super helpful when we start doing more complicated problems. One thing that you're going to be doing possibly for one of your lab assignments is actually working with a chart. And so I've provided some video on, how to work with a chart. This is essentially the same idea, but utilizing a tree diagram. So let's pretend we're going to toss a coin. There are 2 branches. I can either go this direction and I end up getting a heads, or I can go this way and I end up getting a tails. And then I actually write their probability on each branch, which both in this case have a half chance of occurring. Now, it's good because if I want to toss the coin a second time, I now have gone my first toss, and now from that toss, I toss again, and I can either get a heads or a tail. And so you'll notice again on all the branches, I've put their probabilities. But then this allows me to say, okay, I either get a head and then a head, or a head and then a tail. Or maybe I get a tail and a head, or maybe I get a tail and a tail. So how do we calculate the overall probabilities? Well, we always multiply along the branches and we add when we go down. So moving in this direction is multiplying. Moving in this direction is going to be adding. So if I want to know what is the probability of me getting a head and another head, I'm going to multiply the first probability, which is 1/2, times the second probability, which again is 1/2, and that's going to get me 0.25. And you'll notice that if I add up all those probabilities, they do in fact equal 1, which is the perfect value. So when I add, that value would not or should not exceed the value 1. The probability of getting at least 1 head from 2 tosses is 0.25. Plus 0.25 plus 0.225, which is equal to 0.75. So looking at this statement right here is where I'm at, where I'm highlighting. So the idea here is what's the probability of getting at least 1 head from the 2 tosses. So this one has a head, this one has a head, and this one has a head, which is why I take the probability of these three and add them together to get 0.75. Independent events are events that do not depend on one another. They don't affect each other. So for example, if I flip a coin 3 times, all their tosses are independent of one another. They don't affect each other. Like, I'm either going to get a heads or a tails, and what I got on my first flip doesn't affect what I get on my second or third flip. So we're off to a soccer game, and we enjoy being the goalkeeper, but that is actually dependent on who the coach is today. So with Coach Sam, the probability of being goalkeeper is 0.5. With Coach Alex, the probability of being goalkeeper is 0.3. Sam is coached more often, about 6 out of every 10 games, which is a probability of 0.6. So what is the probability that you will be the goalkeeper today? So it's really easy to sit down and go ahead and make yourself a tree diagram. So step 1 is that we know we have 2 coaches, and we're just told that Sam is coached more often, about 6 out of every 10 games. So that's 0.6. So notice that I started by making my tree diagram with Sam and with Alex, and I put 0.6 for Sam. So how did I get the probability for Alex as 0.4? Well, I know that if the probability in total has to equal 1, I can subtract off the probability that Sam is the coach, and that's going to give me the leftover probability value of 0.4 for Alex. Now, being a goalie. With Coach Sam, the probability of being goalkeeper is 0.5. So 0.5 if I am the goalkeeper. 1 minus 0.5 leaves me with 0.5 for I'm not the goalkeeper. With Coach Alex, the probability of being goalkeeper is 0.3. So I'm going to draw an arrow that says 0.3 for yes. So what do you think my no probability value is going to be? If you said 0.7, great job, because I did 1 minus 0.3. So now I can find the probabilities. So the chance of Alex being the coach and I being the goalkeeper is 0.12. The chance of Alex being the goalkeeper and me not be, or excuse me, Alex being the coach and Alex not allowing me to be the goalkeeper would be 0.28. So any values that I'm finding across, I'm just multiplying them. Now, if I want to know what's the probability of being a goalkeeper today, I'm not concentrated on who's the coach. I don't care. That's irrelevant information to me. I only care about what are the chances that I'm the goalkeeper. I'm going to focus on this portion here with Alex because that's a yes that I'm the goalkeeper. I'm also going to focus on this part here with Sam because this is also that yes, I am a goalkeeper. And I'm going to take my value 0.3 and 0.12, add them together to figure out that I have a 0.42 chance of being goalkeeper. And if I want to write that as a percentage, I can move my decimal 2 places to the right, and that's 42% chance. Now, there's something special called the fundamental counting principle. This is super helpful. When there's m ways to do one thing and n ways to do another, all you have to do is multiply the 2 values to figure out how many options there are. So I like thinking about this with clothes. I always think that that's the easiest to think about when you're dealing with the fundamental counting principle. If I got like 5 shirts and 10 pants and I want to figure out how many different combinations of outfits can I make with 5 shirts and 10 pants, I just do 5 times 10, which is 50. So there's 50 unique outfits that I could create. So here's another example, 3 shirts and 4 pants. That means there are 3 times 4, which is 12 different outfits. You have 6 flavors of ice cream, 3 different cones. 6 times 3 is 18 unique single scoop ice creams. A little more complex, you're buying a new car. There's 2 body styles, sedan or hatchback. Then there's 5 colors. Then there's 3 models. So how many total choices do you have? So you got your new car. You can either have the sedan or the hatchback. Then each of those has the color options, and then each of those has the model, right? So that's a lot of different options to sit there and try to figure out by hand. So instead, you can say, all right, sedan or hatchback, that's 2 times 5 different colors times 3 different models. There are going to be 30 unique choices. But it only works when all the choices are independent of each other. If one choice affects another choice, so it depends on one decision that you make, then a simple multiplication is not right. So let's say that black is not an option for the hatchback vehicle. So you can have black for the sedan, but not for the actual hatchback value. Because your choices are not independent of each other, you still can use the fundamental counting principle. You just have to do it a little differently. So you have 5 different colors over here and 3 different models for each of those. So you can multiply that together. You have 4 different colors on this side with 3 different models each. So you can multiply that together. And that gets you your 15 plus your 12 value. And when you add those together, you get a probability value of 27. On this last slide, I encourage you to look at the application section in your textbook on page 330, looking through numbers 1 through 3. You do not need to turn these in when you're finished, but I do encourage you to try to do these to the best of your ability. As always, if you have questions or concerns, please don't hesitate to reach out to me, and I hope you all have a wonderful rest of your day.